Hi, Al. You asked me to help you out a little bit on 3.4, so I'm going to put a little video together for you. 3.4 talks about linear functions, and linear has as a root the word line, and that's important because linear functions are functions that when we put them on a coordinate plane would make a line, a nice straight line. When we graph them. And later on, we'll get into graphing linear functions. But this is just kind of an introduction into what a linear function is. And so the most important thing to remember about a linear function is that when we put all the points that would be xy pairs, x and y values, when we graph them all onto a graph, they're all going to line up in a nice line. Without graphing it, can we tell if a function is linear just by looking at the values of a table? Yes, we can. And here's how we do it. I'm going to go a little bit off from the book, and there's a good reason that I do that, because I want to talk a little bit about the idea of change. A long time ago, when people first started to look at linear functions in ancient Greece, we'll go back to that time, they used a symbol called delta. Delta means change. So we can look at change in the y values and compare it to change in the x values. So when I put that little symbol, it's a triangle. It's the Greek letter delta, and it represents change. What we're interested in here is how much change is there in the y values, say from 6 to 8, and how much change is there in the x values that correspond with that from 1 to 2. If we look at this ratio, we're building a fraction, the change of the y values over the change in the x values. To get from 6 to 8, that's a change of 2. To get from 1 to 2, that's a change of 1. So if I look at the change in the y values and compare that to the change in the x values, it's a 2 to 1 ratio. I'm going to do that for each of these values in the table. That is, I'm going to pair up the 6 and the 8, compare it to the 1 and the 2. Then I'm going to pair up the 8 and the 10, compare it to the 2 and the 3. Then I'm going to compare 10 to 14 to 3 to 4. Okay, so let's take a look. How do we get from 8 to 10? Well, again, that's a change of 2. And how do I get from 2 to 3? Again, that's a change of 1. And finally, let's look at how we get from 10 to 14. To get from 10 to 14 is a change of 4. And to get from 3 to 4 is a change of 1. Now, in order for the function to be linear, in order for it to be a line when I draw all the points on the plane, the change, that ratio of change to y to change to x, would have to be the same in each of these cases. 2 to 1, 2 to 1, 4 to 1, not the same. Therefore, this table does not show a linear function. This is not linear. If it was, I would have seen the same ratio, 2 to 1, 2 to 1, all the way through. Let's take a look at the second table. Again, I'm interested in the changes in the y's over the changes in the x's. I'm going to build these fractions. To get from -6 to -3, there's a +3 change. To get from 2 to 1, there's a -1 change. negative 1. Let's look at the next one. How do I get from negative 3 to positive 3? Well, that's actually a change of positive 6. How do I get from 1 to negative 1? Well, that's actually a change of negative 2. Let's look at the last grouping. How do I get from 3 to 12? Again, I'm not looking to multiply here. I just want to know how far, or what do I add to it to get there? How far apart are they in the number line? To get from 3 to 12, I'd have to add 9. And then to get from negative 1 to negative 4, I'd have to subtract 3, or change a negative 3. Now, these don't look the same, but I wonder if I can reduce the fractions. Of course, 3 over negative 1 is the same thing as negative 3 over 1. 6 over 2, there's a common factor of 2, and I can take that out, and I'll be left with negative 3 over 1. In other words, the fraction 6 halves reduces to 3 over 1. And finally, 9 over negative 3 also reduces to a negative 3 over 1. So for this second one, notice that in reality, that change of y over the change in x is the same for all of my groupings here, okay? And when that's true, we can say that the function is linear. So we have this test to see if something's linear. I look at the change of y over the change in x for each pairing that I can do here. negative 6 to negative 3 compared to 2 over 1, negative 3 to 3 compared to 1 to negative 1, and 3 to 12 compared to negative 4, or negative 1 to negative 4. If they're the same each time, I can say it's linear. Linear functions, when I plot the points, because each one of these is going to have an x and a y, remember when we did like that graffiti exercise where we were plotting all the xy points? We connected the dots. If we did that, if we plotted the point 2, negative 6, the point 1, negative 3, the point negative 1, 3 as xy pairs on the coordinate plane, if I connected them all together, they would form a nice straight line, and therefore that's a linear function. That's our test for linear functions. Let's go on to the second part that they talk about in your book, and that is what is a discrete function versus what's a continuous function. To do that, I'm going to use the example of, let's say, a little swimming pool, maybe big enough for your dog to fit in or something, not too big. We want to keep things on a small scale. And there's two ways that we could go about filling this little pool. The first way is we could maybe get a bucket, and we could fill up our bucket, and then we could dump the bucket into the pool. Now I want you to think about the height of the water inside the swimming pool. If we think about the water level, the height of the water inside the pool, and how it changes when we're filling it with a bucket, I think we can see that, like, when I put one bucket in, it's not going to be very full, right? But it went from being completely empty to having a little bit of water in it. Then I put another bucket in, and it went from having a little bit of water to having a little bit more. If I were to sort of graph this idea, I could have a little graph that says, all right, time that it takes to fill my swimming pool on the bottom, and height on the side. It starts off at 0, right? 0 height. I haven't put any water in. And then I pour a bucket in, and suddenly the height of the water raises instantaneously. I just pour that bucket right in, just dump it in, and suddenly that pool has some water in it. There's a height to that water. And then I dumped the next bucket in, and it went from that level, it instantaneously goes up to another level. Okay? Enough time to fill my bucket, and I go back and I pour it in again, I dump it in, and that height goes boom to the next level, and it's going to stay there until I pour the next bucket in. This situation is called the discrete situation. It comes in distinct steps. There wasn't any water in it, boom, there was water in it, and it stayed at that level until boom, I made the change, and the next level occurred until boom, I make another change and I'm at a different level. Anything that can follow this sort of stair-stepped pattern is called discrete. Okay? Let's look at a different situation. Instead, suppose that I grab my garden hose and I pour that, or I put it into the pool, turn on the water, and now let's think about how that changes our graph. Again, let's put time on the x-axis and height on the y-axis. I put that hose in, I turn the water on, and it goes from 0 up steadily until such time as I were to turn it off, right? But this idea of filling it or changing the height over time is going to look very linear, right? But there's no steps. It's just continuously filling with water. It's continuously getting higher in its water level. Look at the difference between the two of them. Now, the points themselves, if I look at the points that sort of would make this graph, right? There's definitely something that looks the same here if I were to just plot some points on there. They would look very much the same. Notice the point 1, 1 is in both of these, 2, 2 is in both of these, 3, 3 is in both of these, 4, 4 is in both of these. They're completely different situations, but they really do contain the same points. The reason that we have to think about discrete versus continuous is that situations are different, and the models to model those situations have to take on the characteristics that we need. A discrete function is going to look very stair-stepped. I can't just connect the dots. It's misleading if I make this graph look like this graph by simply connecting the dots. Because in this situation, it's not a continuous function. It was at one level, then boom, it's at another level, then boom, it's at another level. That happens sometimes in real life. And so our mathematical model needs to represent that as well. The reason your book kind of wants to distinguish these is because we as humans just would like to connect the dots all the time. And that's not the best way to do this. Before we can draw the line for some function and just connect our dots, we have to consider the situation. It wouldn't make sense to just draw a line through all of these dots, because that's not what really happens when you think about filling the pool with a bucket. On the other hand, sometimes it makes perfect sense to connect the dots, because this situation is what would occur in a continuous situation or a continuous function where the hose is filling the water continuously instead of doing it kind of in chunks with the discrete function. So the difference between discrete and continuous is that idea of discrete being more of a stair-stepped approach to things, where it's not just a nice continuous line, but continuous meaning, yeah, you can go ahead and connect all the dots because it's continuously changing from one point to the next. Okay, hopefully that clears some of that up. Good luck to you, and hopefully we'll talk at you real soon. Bye.